So this video is about growth and decay models. So first, let's take a look at B. So if B is greater than 1, the function is increasing and it's called exponential growth. So in this case, this was 2 to the x, and then they graphed it. So that's exponential growth. Okay, now B in this case is 1/2, which is between 0 and 1, which means the function is decreasing and it's called exponential decay. So we've already gone over these two things for the past 2 days. So let's just look down here and let's figure out what's growth and what's decay. So on number 1, we have a 3 and we have a 2/3. So out of these two things, remember it's always a, b to the x. If there is no a, it's considered 1. So we're only looking at the b, which is directly attached to the exponent. So in this case, we're looking right here at the 2/3. So 2/3 is less than 1. If you're not sure, go ahead and just plug it into the calculator. So 2/3, and it gives it to me as a fraction, but remember, you can use this toggle button right here above the enter, and it'll make it into a decimal. So since it's 0.66 repeating, that's less than 1, so it is going to be decay. Okay, on the next one, it's 8 to the x. So 8 to the x, there's no a, but that's okay. We only care about the 8. So 8 is a big number. It's greater than 1, so it is growth. Go ahead and pause this video and you guys try 3 and 4. So when you tried 3 and 4, 3 should have been decay because it's 1/2, and 4 should have been growth because the base is 2. So next, let's look at linear function or exponential function. So remember, exponential functions, it has the x in the exponent. So if it doesn't have the x in the exponent, then it's not exponential. If it has the x just right next to it, like number 5, it's not in the exponent, then it is linear. So number 5 is linear because it's not in the exponent. Number 6 has the x in the exponent, so it's exponential. Okay, you guys go ahead and pause this video and figure out 7 and 8, right? If it's linear or exponential. So 7 should have been exponential because the x is in the exponent, and 8 was linear because it's just 2 over 7x minus 3. So what that means is when you're graphing them, this graph is going to be a straight line, while this one, because it's decay, is going to be a curvy line going down. So that's just kind of a review of what we've done for the past couple days. Now we're going to actually look at the growth and decay models. So you get these equations where y is your balance, a is your initial value, r is your percent of increase, it's your rate, but you always have to write that as a decimal. And then your t is your time, and the whole thing inside this 1 plus r is your growth factor. So we're going to use these on the other side. So let's go ahead and look at some problems. So I'm going to go ahead and write it. Y equals a 1 plus or minus r to the t. So I put plus or minus because it can either be increasing or decreasing. It just depends on the word problem. So let's see. Let me focus this a little better for you guys. So on this problem, it says, in the last 10 years, an initial population of 44 deer in a state park grew by about 8% a year. So we know it's growing, so it's going to have to be addition. This 8% right here, that's going to be our R, but we have to change it to a decimal. So if you're not sure how to do that, you can use your calculator. So you're going to press 8 because it's 8%, and then you need to press the second button because we're getting to this right here. So 8, so second, and then we're using the parenthesis above the 8 because above that parenthesis is the percent button. So 8% and then press enter is 0.08. You can also take 8 and divide it by 100 because percent means per 100. So, excuse me, it says, write a model given a number y of deer after t years. So we're just going to plug in to the formula. We're not putting in for time yet. So y equals, A is my starting amount. So it says the initial population was 44. So that's going to be our A. So 44 times 1, and we said it was plus. The rate R was our decimal, 0.08, raised to the T, because we don't know time yet. Then it says, what is the growth factor? Well, if we go back to the other side, the growth factor is the 1 plus R, so it's that whole parentheses part. So our growth factor is 1 plus 0.08, but we're going to simplify that. So 1 plus 0.08 is just 1.08. And it's a growth factor because it's growing. It is greater than 1. Okay, number 3. About how many deer were in the park after year 5? So 5 is what we're going to plug in for T. So using number 1, we're going to rewrite it, but we're going to plug in for T. So you're going to do 44 times 1 plus 0.08 raised to the 5. And then you're just going to plug that in on the home screen. And remember, to get the exponent, you use this little button right here. It's called a caret key. So that's what you should see on your calculator. And then press enter. So it's 64.65 approximately, but they're deer. So you don't round deer. Whenever you have a living creature, whether it's bacteria, a person, an animal, you always what we call truncate. So truncating means you take the decimal off. So we're going to truncate it. So the actual answer is going to be 64 deer. Okay, then it says, in what year will 200 deer be added to the park? So let's go ahead and we're going to use our table function. So we're going to use this button right here. So click it. If anything's in it, delete it out. And we're typing in our original equation. In this case, we can't use T in the calculator, so we're just going to use X. So 44 times 1 plus 0.08, caret key, and your X button is the third button up on the left. So that's what you should see. Enter. We want to start at year 0. Enter, 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 enter. So at year 0, at the initial, there's 44 deer. At year 1, there's about 47. So let's keep scrolling until the right side becomes close to 200. So let's just keep scrolling. Oh, there we go. So at 19 years, there's about 189 deer. At 20 years, there's about 205 deer. So in what year will the deer be added? I'm going to say between 19 and 20. So it's not an exact number because the 200 wasn't exactly on our table. So it's between 19 years and 20 years. Okay, let's go to this next one. A 2010 Honda Accord depreciates at a rate of 11% per year. The car was bought for $25,000. So we need a couple things. We need to know the A, the R, and that's all we know right now. So the A, remember, is your starting amount. So your starting amount is $25,000. That's what it was bought for. Your rate is 11%, but remember, you need to make that into a decimal. So go ahead and make that into a decimal. When you do that, your calculator should tell you 0.11. There's also one more thing we need to know. Is it going to be a growth model or a decay model? Is it plus or is it minus? Well, this word right here, depreciates, means you're losing value. So we're going to have to use a minus sign. So y equals your starting amount, $25,000, times 1 minus, because it's depreciating, 0.11 to the t. Whenever it says write a model, you're always going to keep t. Okay, what is the decay factor? Well, remember, the decay factor is your base. So in this case, it's 1 minus 0.11. So in your calculator, let's do, so clear that out, quit. 1 minus 0.11 is 0.89. So the decay factor, or the base, is 0.89. So how much is the car worth in 2011? So 2011, and it tells us up here, it's in 2010, right? And it tells us right here too, after 2010. So in 2011, only 1 year has elapsed. So your time we're plugging in is 1, because only 1 year has gone by. So what we're going to do is 25,000, 1 minus 0.11 raised to the 1. And we're going to type this into our calculator, and it's money. So whenever it's money, you're going to round to 2 decimals. So let's go ahead and plug that in. 25,000, 1 minus 0.11 raised to the 1. So in this case, there are no decimal places, which is nice. So it is worth $22,250. How long will it take for the car to be worth half of its original price? Well, we bought it for $25,000. So half of that, if you're not sure, do 25,000 divided by 2. So we're looking for when it's worth $12,500. So we're looking for $12,500. And again, for this, we're going to use the table because we don't have time. When you're looking for time, you're going to use the table. So let's go back to our table. Okay, let's delete what's in there. So we're using 25,000. 1 minus 0.11, caret key x. Start at 0. And go ahead and pause this and scroll until you find the year. Okay, so it should be between 5 to 6 years because at year 5, it's worth $13,960, and at year 6, it's worth $12,424. So between year 5 and 6. Okay, next we have an extension. It's going to be the last thing. I'm going to try the last problem on your own. What would the value use for a growth factor if the principal is being doubled every year? So doubling means you're multiplying everything by 2. So your base is going to be 2. Okay, what happens if you're tripling it? Then it's going to be 3. So over here, your equation is going to be a times b to the x, where a is your start and b is triple. So 25 times 3 to the t.